Welcome back to 6-Minute Tutorials. Today I'm going to be covering the basics of related rates. So we need to understand two major parts of just simple equations before we can get into related rates. Related rates deals with static equations and dynamic equations. A static equation would, for example, be the area of a circle equals pi r squared, or the volume of a cone is pi r squared times height over 3. An example of a dynamic equation would, for example, be dA dt. So this is the rate at which the area changes with respect to time. And we could say, for example, 2 pi r times dr dt. So this specifically is the general dynamic equation for the rate at which the area changes with respect to time. And if this equation right here looks familiar, this is just the circumference of a circle. And then you're also multiplying by dr dt. So let's kind of talk about taking the derivative of something with respect to something else. So usually when we do d over dx, okay, what we're putting here is a curve, okay? So whatever it may be, if we're taking the derivative of y equals 5, right, we know that the derivative is 0. The derivative of this curve, what is that curve? 1, 2, 3, 4, 5. Apologies for the poor drawing, but this is y equals 5, right? This graph right up here. And this is what we call a curve. Even though it's a straight curve, I mean, it is a straight curve because the derivative of this is 0, which means its slope is 0. So whenever we're taking the derivative of something, that something is referred to as a curve. It's not necessarily always a function, and I'm going to demonstrate that right now. So let's say we have this equation, x squared plus y squared equals 25. So this is the equation of a circle centered at the origin with a radius of 5. So if we were to draw that, that would look something around that, we could say. I'm not necessarily the best drawer, so I mean, it's a little better, I guess. And if we were to take the derivative of this curve, okay, so the derivative of this curve, x squared plus y squared equals 25, with respect to x, okay, so comparing the rate at which the curve changes compared with x, we would get 2x plus 2y times dy dx equals 0, okay? And the reason we don't put anything in front of the 2x is that we actually have an implied times 1 there. So we're actually saying here 2x times dx over dx, so the rate at which x changes with respect to x, that's going to be the same thing. So we don't even show this. And then this here is the rate at which y changes with respect to x, but we have to show that because they're not changing at the same rates. Now, if we did this again, so we had x squared plus y squared equals 25, and we took the derivative of this with respect to y, we would get 2x times dx dy plus 2y, and then we have the implied dy over dy, which would just not show up, equals 0. Finally, let's say we're taking something with respect to time. So x squared plus y squared equals 25. We're going to take the derivative of this with respect to time. So we would put dt on the bottom. And this would be 2x times dx dt plus 2y dy dt equals 0. So if you've ever wondered why we show why we need to have this for these, and why sometimes we don't show dx. Like for example, when we have y equals x squared and we take the derivative of this with respect to x, we only say 2x, even though we have an implied dx here. This is the same thing as just saying times 1. So this is the reason we do that.